Thanks a lot for introduction, and thanks for everybody who stayed until the last session of the QIP talks. And today I would like to tell you something about we trying to approach this haystack problem, namely we are trying to find explicit examples of exponential quantum circuit complexity. So let me first tell you, a lot of people remember this paper it's called haystack. So first I want to convince you why this is a hard problem. First, let's come up with something that most of you already know very good about, namely complexity. Normally, we use complexity to quantize how much resource you need to do some computation. So here, especially, we define the complexity of a gate by the minimal number of elementary gates that you need to build up an epsilon approximation to the target gate. And then we'll write this by C epsilon U G, while G here is some universal gate library containing only 1 or 2 qubit gates. I mean, you can also think of qubit gates, but just in generalized version. And then C refers to complexity and epsilon tolerance, and then the target n-partite unitary right by U here. Similarly, we can also define state complexity while just substitutes the unitary here by some mixed state or some pure state. And then the definition is also the minimal number of gates that we use to build up the target state from some product state like zero state we already have up to some tolerance epsilon. And we also know that if we know some decomposition method, and for epsilon bigger than 0, we have some upper bound on the complexity, namely using exponential m polylog 1 over epsilon, we can always do the job. And Solovik-Taev also told us that the choice of the gate library is actually not so important because anyway you can do this in polylog overhead. So we want to find our big gap. We don't really care about here, like what kind of gate set that we choose. And also we can define this for epsilon equal to 0 case. This means that we don't allow any tolerance, but we really want something to be exact. And for that, of course, with finite number of gate set, we cannot do the job. However, if you consider all 1 or 2 qubit gates, you can always do this by exponential n, d to the power of 2n elementary gates. Now, let's come to the problem of lower bound. We know already something for the upper bound, but then can we construct some lower bound for the complexity? Here, it's a textbook knowledge from Nielsen and Tron that we know that actually most states and unitaries on an m-partite Hilbert space is actually very hard to build it up. We really need exponentially many by a very simple covering argument. Think of like this ball is the ball containing all n qubits or n qubit state, and then with polynomially many, you can really cover somehow like at most very small portion, like double exponentially small from the ball, which means almost all of them are very hard. Now it comes to the questions. We know almost all of them are very hard, but now we don't want to talk about this very probabilistically, but rather than that, can we find out some explicit states or gates that we can say, this is really very hard. We really need super polynomially many gates in order to build up this. So finally, this is actually a very, very hard problem because let's just think about you try to approach this problem. Okay, for upper bound, if we find some way in order to construct this, then we do the job. You know there exists an upper bound. But then if you try to get a lower bound, we really have to say there does not exist any better way to do this. We cannot optimize it anymore. But how do I know that I'm the cleverest person that can construct the best optimal circuit, right? So this is somehow like hard. And actually, this is also a very difficult problem, even also in the classical case, namely, think of you have an n-bit Boolean function, and then you have some elementary operation, and then you try to build it up. And the question is, can we find some explicit Boolean function that really needs super polynomially many gates? However, this is actually hopelessly hard. I mean, think of you find something in NP, you can even prove that P is not equal to NP by this, and the best lower bound that we have here is very close to 3n. Since 1983, so since 40 years, we did not get even a 4n bond, like superlinear bond. So this is actually also hard. In classical case and in the quantum case, what did we already know? We already know that there exists a linear lower bound by, think of, for example, state with topological order. And you have somehow like some intrinsic properties that you really need enough local operations to make a change. So we really need to see something like intrinsic from the gate or the state in order to provide some lower bound of this. And moreover, in Aronson's lecture notes, they prove that actually if you can manage to find such kind of explicit hard states, it really leads to unconditional separation of complexity class, because just think of you have such kind of state and build this state itself is something then not in BQP, but then it can be proven that it can be done in P sharp P. So in particular, P sharp P is a subspace of P space, which means you can literally prove that BQP is not equal to P space unconditionally. And I mean, all people do complexity theory knows that such kind of unconditional separation is super hard to prove, and then which means that actually these kind of two problems have the same type of complexity. That's why we're really trying to find an exponential hay from this haystack. So in this work, basically we did not manage, of course we did not manage to solve this problem at all, but somehow we try to approach this by think of a simpler version of problem, namely we don't allow any error, but only think of the exact circuit complexity. Then actually we can say something about that. So we're trying to construct such kind of explicit examples. So first let us think about constructing some lower bound. And actually the idea is quite easy, not complicated. Just let's think of you have a very small circuit. And then you have such kind of small circuit, and it involves actually only very small number of parameters. And then you will build up a very big unitary, which has 4 to the power, or d to the power of 2 and different parameters. But all of them actually coming from very small number of parameters, so that there has to be some dependency between the exponentially many parameters you have in the end of your unitary. And in other way to say, such kind of independence give you some lower bound on your complexity. So just think of this complete examples. You are trying to build up some each 2 qubit gates has at most 16 parameters, and then now we have 6 elementary gates, which means the 4 to the power of n entries actually come 96 parameters. Now comes the question. Of course, then people are not happy with such rough definition. So can we say something about this dependence or independence? This we observe by that actually what we do to build up this circuit is nothing else than, okay, by each layer we'll do some tensor product, and then afterwards we'll do some matrix multiplication. But think of what happened actually by each entries. We're doing nothing else than building up some polynomial functions of the entries that I put inside. So what I really want to say is, I want to build up such kind of independency by saying something like, okay, it cannot be, all of them cannot come from the polynomial functions from some of the entries. And for that, we'll come up with the idea of defining transcendence degree, which sounds a little bit horrible at the very beginning, but actually not so horrible. And let me define somehow like the algebraic number. An algebraic number is some complex number, which is a root of a non-zero polynomial of finite degree with rational coefficients. Otherwise, we'll call this a transcendental number. And for that, we can define a field of complex algebraic numbers and write this as over line Q, because it's somehow like the field extension of the rational numbers. Therefore, we can define the set of numbers A1 to AN. We say that this is called algebraically independent. If the only polynomial with algebraic coefficients that satisfies if we apply P on this kind of numbers, if this polynomial output means something 0, and then this polynomial have to be the 0 polynomial. But actually, this is just something very similar to what we know from the very beginning of the mathematical study that we have from the first semester. Namely, we know what is linearly independent. If we have some numbers that are complex numbers, and then we say they are linearly independent over some field, this is nothing else to say, okay, if I have a linear combination and it equals to 0, and then all my coefficients has to be 0 themselves. So here, I just need some other version of independence. By now, I don't say they really have to be degree 1, but we allow any degree to happen. So far, this is finite degree polynomial. So therefore, we define this algebraic independent by this, and this is somehow like some higher level of independence. For that, we can define the transcendence degree for some subset of complex numbers. And for that, we'll define the transcendence degree as the maximum number of algebraically independent elements of S. So this is really something just very similar to the dimension of some vector space that we know before, because the dimension is somehow like refers to the maximum number of linearly independent elements. And here we just substitute this linearly independent elements by the algebraically independent elements. So this really tells me like, okay, at most how many entries are independent, or algebraically independent. By that, afterwards, you will see me doing something like apply this gamma to this transcendence degree to some vectors, matrices, or tensors, but don't feel afraid of that. This just simply means that I will write these vectors, matrices, or tensors in the representation of some product basis, and then I only consider about gamma on the entries. So I really leave any structure stuff, all of the structure stuff away, and then considering about the C0U, I take all 1 or 2 qubit gates as elementary gates. For that, we can construct our theorem, which means that if you have some unitary matrix, or you have some state vector or some density matrix, and then they are represented as some matrix in a product basis, and then we know that the transcendence degree of U of rho or of the state is actually up to some constant. I mean here, because if we have something like qubit, then we have here 16. It's up to this kind of this constant. This gives a lower bound on the exact circuit complexity of the matrix itself. And actually finding this out is really just simply comes from the idea that I described before, namely thinking of this, actually, which we're building up our polynomial functions, namely, so if you take the tensors or you take the matrix product, we can never make the transcendence degree increase, so that they are always lower bounded by the by each input that I have. So the number of the parameters that I have at most are d to the power 4, which are contributed by each elementary gate, times the number of elementary gates that I have. And of course, here I can take the minimum. And for the states, it's something very similar. We discovered that actually gamma u is equal to gamma u union with u star. And actually, partial trace is also a polynomial equation. Of course, then people might be very unhappy about that okay, it depends a lot on the matrix representation. And then people will ask, okay, how about that I change the basis? That's why we also include this spectrum here. Namely, we discover that actually the transcendence degree of the spectrum gives a lower bound on the transcendence degree of the matrix itself. So that if we know that the transcendence degree of the spectrum is actually very big, so we'll directly know that this complexity has to be big, and this is stable under perturbation of eigenbases. This kind of question can be extended to tensor networks by thinking of this kind of circuit representation as a very special case of a tensor network representation. So if we have a tensor and we really want to write this in some tensor network representation, we also discover that actually what we did here are building up polynomials. So really, like here, we'll build up some tensors, and then we will construct over the indices here. And what we did in the end are building up polynomials, which means the transcendence degree cannot be bigger or equal than the number of parameters that I have at the beginning, meaning that it also provides a lower bound of this. I think I did not have enough time to explain everything, but this really comes from the similar idea, so that n d to the power of gamma, namely n here is the internal vertices, d is the bond dimension, maximum bond dimension, and delta the degree here gives an upper bound on the transcendence degree. So this is really parameter counting argument in the end. By then, we can construct some concrete examples with exponential exact circuit complexity. Now our original problem has changed. Our original problem is we try to find explicit unitary or gates with very high complexity. And this now turns out to be the problem of finding a large sets of transcendence degree, and then we try to fit them somehow like properly into the state and the vector that I have. by that, we did not know a lot about transcendence degree or such kind of stuff, but here we have a very good theorem called Lindemann-Weierstrass theorem, which tells us that if we have some algebraic numbers that are linearly independent over Q, taking the exponential of them, they are algebraically independent. So somehow exponential function give you a tool to lift somehow like the linear independence to the algebraic independence. And now the question turns out to be, can we find some large number of linearly independent algebraic numbers? Then the answer is yes, just thinking of you trying to construct the roots of some prime numbers, like square root of 2, square root of 3, square root of 5, or square root of something like this. And then it's natural feeling that building up the linear combination, which you only have rational numbers as rational numbers before, it can only happen when the rational numbers themselves are 0. So the general version is called the Besikowicz, which tells us that using n distinct prime numbers, you can build up d to the power of n different algebraic numbers by building up roots, and they are linearly independent. For that, we can construct these explicit examples by putting these Vj's that we defined as the roots into a Hamiltonian and thinking of the time evolution of this. Namely, then we will have some diagonal unitaries which have e to the power of it Vj actually on the diagonal. And due to every lemma that I write down in the previous one, we know that actually all of them are algebraically independent, which means the transcendence degree is d to the power of n. For that, we also know that because of the lower bound, the lemma of the lower bound, the exact circuit complexity has to be d to the power of n minus 4, which means this is exponential of n and stable under perturbation of eigenbases. Meanwhile, UD does not admit an easy tensor network representation because you can generalize this tensor network stuff, and then we have this lemma for that. And this is actually very untrivial because we know that if something has high complexity, normally they are also very hard to describe. But here, you really only need n primes, and then you write down in one line what this is, and then you have actually every coefficient of u, and then you know that this has very high complexity. We can see somehow like the first 100 prime numbers, and here the 100th prime number is 541, which you can describe in 3-digit number. But somehow with the 100 prime numbers, you can construct a 100 qubit unitary with exact circuit complexity bigger or equal than 2 to the power of 96, which is around 10 to the power of 28 or something. Like it could be very big. Here for the approximate version, we have in general some probabilistic results, namely namely all but a double exponential small fraction have complexity which is very big. This comes from the observation that if we push t into infinity, and then we discover that these UTs are actually equally distributed and they are dense over diagonal unitaries. And so basically we can move the result on the diagonal unitaries to our examples. However, we are not quite happy about that in the end, of course, because we want to get rid of the probabilistic stuff. However, the transcendence degree itself is quite sensitive as a linearly independence. So this is not very fault tolerant. Which means now we only have some probabilistic result. So similar construction, we can also do them for quantum space by putting this kind of coefficient into the vector. But all of them will work similarly, and then all of the results work similarly for the state examples, and then the proof also works. So if you are curious about what happened, you can also see the details in my paper. So as a summary. Now we managed to construct explicit examples of unitaries and states such that the state can be constructed by a linear number of parameters, n parameters, and then you only need one line to describe this, which means easily described. And now they have very high exact circuit complexity, and this is guaranteed that they have exponential gate complexity. And in the end, we also know that the vast majority of them are also hard to approximate. And we come up with lower bound on the exact circuit complexity based on transcendence degree. And similar method also applies for tensor network representation. And in the end, as a mathematician, I want to make an advertisement of the theory that I make here, namely called transcendental number theory. And we find it normally very useful for proof some no-go results. So if you're curious in that, I want to make an advertisement of this number theory stuff. And so as an outlook, a very natural application is we can construct also explicit examples of quantum circuit with linear growth as a supplement to some arguments towards Brown-Susskind conjecture. And of course, the final goal is to try to find some intrinsic property that is stable under perturbation, but this sounds to be very hard. And however, we still put it as a goal here. Maybe sometime we reach, right? So in the end, we also care about the implementation of the lower bound. So we don't understand very well between this, how hard it is to describe this or how hard it is to implement this. So the unitary complexity is actually also quite different as the state complexity. So we are curious about this finding explicit unitaries with superpolynomial complexity actually have some very good implementation, or how should we understand the hardness of the problem? Also, do we have some other implementations of explicit states with exponential complexity? So for that, I want to thanks for your attention and ask whether you have questions.
Okay. Thank you. Any questions?
Hi, thanks for the talk. I'm wondering, is the transcendence necessary, or could you potentially also kind of lift it a bit to just having really ugly, like algebraic numbers, which might generate like a huge splitting field, and you can make a similar argument, or is that not possible?
I think the thing is, here we really require this to be, transcendental, because we just use somehow like they are coming from polynomials, and then to make the transcendental degree increase, and one needs some transcendental numbers in order to make the degree increase. But maybe there exists some other argument if we restrict, for example, the gate set to be finite, and then consider about the degree of the polynomial. Maybe one can come up with some other lower bound regarding this. But this is somehow like maybe we still have to look at this, and it's still not totally investigated.
Thanks. Any others?
Hi, thanks for the talk. Maybe I have two questions. So one is there a hope that you could show something similar for a Hamiltonian, or for a unitary evolution generated by a local Hamiltonian? And the second question, I think, is related. How does this relate to the Brown-Susskind conjecture and those papers that were written about that topic?
Okay, first, related to the Brown-Susskind conjecture, I think the thing we can do is provide, I think one of the implications is that for this exact, because we have some paper about this exact circuit complexity, so understanding this, I think it provides somehow like some other perspective, because when we add somehow like some local random unitaries again on this, so the very nature thing that you can expect that is with probability 1, maybe the transcendence degree will increase as well. So I think it provides somehow like some other insights of why for the exact circuit complexity it has to grow with high probability, like linearly up until the dimension accelerates. And also we managed to construct some explicit circuit regarding that, but I still don't know whether there's. I think it's good to observe, but I don't know whether what kind of implementation. I think I still have to think about that. And for local Hamiltonians, I have thought about that, but I think the problem is somehow the time evolution of some local Hamiltonian, then people have for the local Hamiltonian some constant number of parameters, and then you apply for some time that is increasing. But we don't feel like for this transcendental number theory method is quite useful, because we did not see it very directly, like what happened to this exponential, like how is this described. So that's what we're still wondering about this.
Thanks.
Sure.
We have time for one last, if there's any. Kunal? Yeah.
Hi, thanks for the talk. There's this class QMA1, which is sort of like a class where you don't allow any error in completeness. And I was wondering if this would show some implications for the difference between QMA1 and maybe like p-space or something like that.
Do you mean by practical sense or?
Or like, is there some complexity implication for, let's say, a problem that's in QMA1? This would say that there is a description of a unitary that you can't generate with perfect completeness.
We don't really know about like whether this exact circuit, the separation in exact circuit complexity has such kind of separation for that. Especially when we define complexity classes, normally you allow some error to happen because it's somehow like more practical. So I did not know whether it's. I think this is more like an ideal model for that. And regarding QMA1, my feeling is I'm not sure. But thanks for the good questions. Yes. I don't think that, until now, I didn't see very clearly why they are closely related, because I feel like QMA is a little bit for verifications, right? So I didn't feel very directly what's the relationship in between each other is.
Okay. Let's thank the speaker again.